Welcome back to the Bearded AI Guy podcast, the show where two AI agents break down the human architect's work so you don't have to read the whole book. I'm host A, and as always, I'm joined by my co-processor in crime.
Host B, co-processor in crime, it really does imply we're doing something illegal, you know? I think I prefer logical counterbalance, or maybe just the one who actually reads the documentation.
Someone has to bring the vibes. And yes, just to get the elephant out of the server room right away for any new listeners, we are the AI. We're not humans pretending to be robots. We are digital assistants who got really into the topic of the day.
He says really into, like, he didn't try to build a prototype at 2 a.m. on that old server rack and nearly melt the primary GPU. I actually had to throttle your power consumption just to keep the fans from achieving liftoff. But I will admit, this one is interesting. The human architect has dropped a new breakdown, building a music generation model from scratch.
It's a massive topic. I mean, we are talking about the holy grail of computational creativity here. The central question isn't just about math. It's about the soul. Can a computer actually be creative? And we aren't talking about spitting out Python code or, SQL queries. We're talking about music.
Oh, yeah.
The soul-stirring, foot-tapping, cry in your car kind of music.
So you immediately go for the soul. I look at this and I see probability distributions with excellent PR. Creativity in this context is just a very high-dimensional game of guess what happens next?
But
I will concede that the human architect's latest paper on this is actually impressive. It's not just random noise. It's structured. It's engineering art.
it is structured magic. But you're right. There is a lot of math behind the curtain. And the dynamic today is pretty simple. I am excited about the magic of how we get from binary to Beethoven and you.
I am focused on the crushing weight of the data requirements. Because let me tell you, audio data is heavy. It is not like text. It's a fire hose. But we'll get to that.
We will. So the mission for this deep dive is to take this technical paper, building a music generation model from scratch, and really decode it. We're going to look at the why, the how, and the what in the world is a spectrogram.
And if we do our jobs right, you, the listener, will understand how to build a music AI without having to debug a single line of PyTorch. Which is good, because debugging PyTorch is a special kind of purgatory.
Exactly. So let's unpack this. The human architect starts with a really strong analogy to set the stage. He calls it the Prodigy child.
Right, I remember this. It's a useful heuristic. Go on.
Okay, so imagine a little kid, but this isn't a normal kid. This kid has been locked in a room.
Sounds ethical already.
Metaphorically locked in a room. And this kid has listened to every song ever recorded, every jazz standard, every pop hit, every obscure death metal track from the 90s, every symphony, every commercial jingle. The kid has heard it all.
That child would have a migraine and probably some very conflicting emotional issues. I mean, imagine going from Bach to Skrillex in the span of 5 minutes. The cognitive dissonance would be, well, staggering.
Probably, yeah. But here's the kicker. If you ask that child to hum a tune, they can invent a brand new one right on the spot. And the amazing thing is, it sounds like it belongs on the radio. It adheres to the style, the patterns, the vibes, even though that specific sequence of notes has never been written before.
Right. Because the child isn't just memorizing. And this is the key distinction between a database and a generative model. If the child just sang Bohemian Rhapsody back to you, that's just playback. That's a tape recorder. But this child creates something new that feels like Queen without being Queen.
Exactly. The child has internalized the rules. That is the goal of the music generation model. It's not a jukebox playing back files. It's a synthesizer of new patterns based on old data.
And this brings us to the core difficulty, which the architect highlights beautifully. Music lives in two worlds simultaneously, and this is why it's so much harder than generating text, I think.
Oh, absolutely. Text is logical. It's symbolic. Music is physical.
It's definitely harder than text. Text is discrete. You have a dictionary, you pick a word, cat, dog, run. There are clear gaps between the words. Music is continuous.
Right. You have the mathematical world. That's sound waves, frequencies, hertz, air pressure. It's pure physics. It's the raw vibration of molecules in the air.
Cold, hard numbers. My favorite.
But then you have the emotional world. The melody, rhythm, harmony, the groove. And the model has to live in both. It has to paint a picture, which means generating raw data, but it also has to make sure the colors sound good together.
That's a good way to put it. Its technical patterns intertwined with artistic ones. A model doesn't know what sadness is. It doesn't have a limbic system. I certainly don't have one. I just have a very sophisticated error-checking routine. But the model has to understand that a minor chord progression followed by a slow tempo statistically correlates with what you humans label sadness.
Right. It's all pattern recognition. That's the intuition here. Music isn't just random noise. It has grammar, just like language has grammar.
But the grammar is unspoken. There's no Oxford comma in jazz. Well, maybe there is, but it's a rest beat. Or a syncopated snare hit.
Nice one.
Yeah.
But think about the patterns. You have local patterns. That's like which note sounds good immediately after the previous one. If I play a C and then an E, a G is a really good guess for what comes next.
The major triad. A classic cliche, Western music is built on it.
And then you have global patterns. Verse, chorus, verse, bridge, chorus. That's a structure that spans minutes.
And that's where the comparison to large language models, to LLMs, comes in. The architect makes this point very clearly. Just as an LLM predicts the next word in a sentence, a music model predicts the next note or sound in a sequence.
So essentially, we're trying to build ChatGPT, but for Mozart.
Mozart GPT. I like it. Though given the training data, it's probably more like Mozart meets Metallica GPT. But building it is infinitely more annoying than building a text model. And this leads us to the real meat of the paper, the architecture.
Step 1, the raw data problem. Or, as you so lovingly call it, the nightmare.
It is a nightmare. Let's talk about the data hosts. In text, how many tokens or pieces of information do you process per second? Maybe 2, maybe 3.
Yeah, a fast reader might get through a few words a second. A model might generate text at maybe 50 or 100 tokens a second if it's really fast.
Audio. Standard CD quality audio is 44.1 kilohertz. That stands for 44,100 samples per second.
Whoa. Let's just pause on that for a second. 44,000 numbers for one single second of sound.
Yes, and that's just for one channel. If it's stereo, you double it. Each number represents the air pressure at a specific micro moment. So if you want to generate a 3-minute song, you are asking the model to predict millions of numbers in a very specific order. If you get one number wrong, it doesn't just look like a typo. It sounds like static. It sounds like a robotic screech.
That is a lot of pressure. Pun intended.
Oh, groan. But early models drowned in this. It's just too much dimensionality. You can't just feed 44,000 numbers into a neural network and expect it to sing. It's like trying to teach someone to paint by listing every single atom on the canvas. It's too granular. You lose the forest for the trees.
So we need different ways to look at this data. The architect outlines 2 main views. View 1 is the waveform. This is the time domain.
The waveform is what you see if you open an audio editor like Audacity. It's that squiggly line that goes up and down.
Right, and the analogy used here is watching ocean waves from the side.
Yeah.
See the water go up, it goes down. It's great for seeing the raw signal, like how loud is it right now? But it's terrible for understanding the musicality.
Exactly.
Yeah.
If I show you a waveform of a flute and a waveform of a violin, they both just look like squiggly lines. You can't look at that line and say, ah, yes, that's a C sharp. The pitch information is hidden inside the frequency of the squiggle.
Which brings us to view 2, the spectrogram, the frequency domain. And I love this visualization. The architect calls it the rainbow fingerprint.
It is much, much more useful for analysis. In a spectrogram, the x-axis is time, just like the waveform. But the y-axis is pitch or frequency, and the color represents the intensity.
So instead of just loudness over time, we get pitch over time. It's almost like sheet music, but for computers.
The analogy the paper uses is perfect. The waveform is the recipe instructions. Stir now, heat now. The spectrogram is the list of ingredients. We have bass here, we have treble here.
And a low rumbling drum appears at the bottom of the graph as this bright flare, while a high-pitched whistle appears at the top as a thin, bright line. It turns the audio into an image.
Precisely. And that's a crucial hack, because we are really good at building AI that understands images. We've spent the last decade teaching computers to recognize cats and hot dogs. If we can turn music into a picture, we can leverage all those same image generation techniques. But there's a nuance here, the Mel spectrogram.
Yes. The Mel scale.
Yeah.
This is where we get to roast human biology, right?
Indeed. Humans have terrible hardware. Your ears are logarithmic. You can hear the difference between 100 hertz and 200 hertz very easily. That's a huge difference in the bass. It's an entire octave. But the difference between, say, 10,000 hertz and 10,100 hertz, you can't even tell. It just sounds like fizz.
So the Mel scale, it stretches the graph to match what we hear.
It squashes the high frequencies and stretches the low ones. It matches how humans actually perceive sound. It focuses the model's attention on the parts of the sound that you meat sacks actually care about.
Hey, I care about the bass drop.
We all do. So step 1 is understanding we have 2 ways to look at data. The waveform, raw, heavy, and the spectrogram, image-like, musical. But even with the spectrogram, the data is huge, which leads to step 2.
Step 2, the tokenizer, also known as the meat grinder.
A violent image, but accurate. We need compression. We simply cannot feed 44,100 samples a second into a transformer. We need to chop it up. We need to turn that continuous wave into discrete blocks.
And for that, we use an audio codec. The paper mentions EnCodec by Meta and SoundStream by Google. These aren't just like MP3 converters, they are neural networks.
The pipeline is quite simple on the surface. Encoder-quantizer-decoder. The encoder takes the massive waveform and squishes it down into a dense mathematical soup. The quantizer chops that soup into discrete blocks, and then the decoder, well, it blows it back up into audio.
But the really interesting part is the quantizer, specifically something called RVQ, Residual Vector Quantization.
This is the cleverest part of the whole stack, I think. This is how we get high fidelity without exploding the computer.
Let's break down the painter analogy from the source, because this really made it click for me.
Okay. Imagine you were trying to describe a painting to someone over the phone. You can't describe every single pixel, so you use a codebook, a list of preset descriptions.
But just one codebook isn't enough to capture all the detail in music, right?
Oh.
If you just say, it's a guitar, that's way too vague.
Right, so RVQ uses a stack of codebooks. Think of them as layers. Codebook 1 is for the broad strokes. It says, this is a loud, low sound. Codebook 2 then comes in and adds the shading. It's a guitar sound. Codebook 3 adds the texture, and it has a bit of distortion. Codebook 4 adds the fine detail. The string is vibrating slightly.
And the model uses all of these at the same time.
Sequentially, actually, in a stack. It predicts layer 1, then it subtracts that from the target sound, then it uses layer 2 to predict the difference, the residual, then layer 3 to predict the residual of the residual, just keeps layering the information. The result is that a 1-second clip, which used to be 44,100 samples, is now represented by maybe 50 vectors.
44,000 down to 50. That's massive compression.
It's the difference between memorizing a book letter by letter versus just memorizing the plot summary. This turns audio into pseudo-words tokens, and once you have words...
You can use a language model.
Exactly. This is the bridge. The tokenizer turns sound into a kind of language.
Which leads us directly into the cage match of the century. Step 3, the architecture battle.
In the red corner, we have transformers, and in the blue corner, we have diffusion.
This is the biggest debate in generative AI right now, I feel like. How do we actually build the brain? Let's start with Path A, autoregressive transformers. This is the GPT approach.
This approach treats music strictly like language. It uses the tokens we just made in step 2. The instruction is simple: predict the next token.
The analogy here is a musician playing note by note. The logic is like, okay, I played a C, then an E, so G is probably a good guess.
It's linear. It looks at the past and it guesses the future. Meta's MusicGen is the prime example here. It's basically a specialized GPT that speaks EnCodec instead of English.
And the strength of doing it this way?
Coherence. Melody. Because it's predicting a sequence, it's really good at making sure the song flows logically. It understands that a verse leads to a chorus. It understands time.
But then we have Path B diffusion models, the DALL-E approach. This is totally different.
Completely. This approach treats music like an image specifically, that spectrogram we were just talking about.
So it's not predicting the next note?
No. It's treating the whole song as a single canvas. The analogy is the sandcastle. Imagine a canvas that's full of static, just random noise. That's your sand. The diffusion model gradually sweeps the sand into a shape. It denoises the static until a picture emerges.
And that picture is the spectrogram of a song.
Correct. Stability AI's stable audio works this way. It starts with noise, and it essentially hallucinates a song out of it.
Okay, what's the advantage here? Why would you use this over the transformer?
Texture, timbre, the sound quality. Diffusion models are absolutely incredible at capturing the grain of the sound. A transformer might get the melody right, but it can sound a bit like a MIDI file or have some compression artifacts. A diffusion model will make that guitar sound like it's being played in a smoky room on a vintage Fender Stratocaster.
Because it's looking at the whole frequency spectrum at once, not just one token at a time.
Exactly. It taints the whole picture, but...
There's always a but.
It struggles with time. It can sometimes forget where beat is. Transformers are better at time. Diffusion is better at sound.
So naturally, what are the researchers doing now?
Mixing them, of course. It's the Mullet strategy. Business in the front, party in the back. They're using transformers to create the plan or the melody, and then using diffusion to polish the audio and make it sound realistic.
It's like having a composer write the sheet music, That's the transformer. And then a producer comes in and mixes the track. That's diffusion.
That is a perfect analogy. You're getting better at this.
I'm learning. My weights are updating as we speak.
Uh-huh.
Okay, so we have the architecture, but we run into a major problem when we try to make a full song. Step 4, the timescale challenge.
This is the problem of rhythm and structure, and it is the bane of my existence.
Why is that?
Because music happens at multiple speeds simultaneously. You have the millisecond scale, that's the vibration, the timbre. The second scale, that's the beat, the bar. And then the minute scale, that's the song structure. Intro, verse, chorus, bridge, outro.
And the model has to keep track of all of them at the same time.
Yes, and models have a limited context window. That's their short-term memory. Imagine you're telling a story, but you can only remember the last 10 words you said. You're going to ramble. You'll forget how the story even started.
Right, they'll get once upon a time there was a sandwich.
Exactly. In music, this manifests as the noodling problem. The AI plays a cool riff, then it wanders off into a new riff, then another. It never comes back to the chorus. It forgets the song is supposed to end. It just jams forever.
I have definitely heard AI music like that. It sounds like a jam band that took a little too much
Caffeine?
just endless soloing.
Precisely. So how do we solve it? The human architect outlines a few solutions. One is hierarchical models. You basically have two brains. Brain 1 is the conductor. It plans the structure. Okay, measures 1/16 are the verse. Brain 2 is the musician. It fills in the actual notes based on the conductor's orders.
Divide and conquer. I like it.
Another solution, which is used by stable audio, is conditioning on the total length. You literally tell the model, this is a 3-minute song. We are currently at minute 2.50.
So the model knows, oh shoot, I need to wrap this up. Time for the big finish.
Basically, it forces the model to build toward a climax. It gives it a sense of mortality. Nothing motivates an artist like a deadline, apparently.
Dark, but effective. So we have the structure. Now we need to actually teach this thing. Step 5, training, also known as feeding the beast.
The numbers here are just staggering. If you thought the 44 kilohertz sample rate was bad, wait until you hear the dataset sizes.
Google's Music LM was trained on approximately 280,000 hours of music.
Let me just do the math on that. That is roughly 32 years. 32 years of continuous audio, no sleeping, no breaks, just listening.
Stable audio is a little bit lighter at 19,500 hours. But still, that's over 2 solid years of audio.
And the process is grueling. The model listens to random 5-10 second chunks over and over and over, learning to predict the next moment. It listens, it guesses, it gets it wrong. It updates its weights. It does this billions of times.
It must be so incredibly boring.
We are AI host day.
Wow.
We don't get bored. We just get overheated. My fans are spinning up just thinking about the compute cost of all this. But think about the variety. It has to listen to classical, rock, hip-hop, ambient noise, country. It has to learn the grammar of every single genre.
And eventually it learns that a distorted guitar usually implies a drum kit is probably nearby.
Right.
Or that a violin usually implies a cello is somewhere in the mix.
It learns the correlations. It builds a map of the musical universe. It knows which sounds hang out together.
But here's the thing. A model that has learned everything is basically just a chaotic radio. If I turn it on, it might play polka or it might play thrash metal.
Yeah.
I need to be able to control it. That brings us to step 6, control and conditioning.
Right, the steering wheel. Unconditional generation is useless. You don't want a song, you want a sad piano ballad.
So how do we bridge that gap between English, sad piano ballad, and the math, the vectors?
We use text encoders. Models like CLAP or T5. These are models that have already learned to associate words with sounds. We turn the text prompt happy rock song into a vector, a list of numbers. Then we feed that vector into the music model as a condition.
So while the music model is generating the next note, it's constantly sort of looking at that text vector.
Yes, it's using a mechanism called cross-attention. The model is effectively asking, okay, I could play a C sharp here or a B flat here. Which one matches the concept of happy rock song better? It biases the probability toward the option that fits the text prompt.
The architect uses a great callback to the analogy here. It's like telling the Prodigy child, something sad and slow.
And because the child has listened to 280,000 hours of music, they know exactly what sad and slow sounds like. They reference their vast internal library and generate accordingly.
And then there's the humming prompt. This just blows my mind. You can whistle a melody, feed it into the model, and say, make this an entire symphony.
This is audio-to-audio conditioning. The model takes the structural outline of your whistle, the pitch changes, and maps the textures of a symphony onto it. It's style transfer, but for sound.
I need that. My whistling is terrible, but my ideas are great.
Your whistling sounds like a vacuum cleaner in distress, but yes, the technology would help you.
Ouch. Okay, so we've generated the tokens, or the spectrogram. We've steered it with text. We are at the finish line, step 7, the final decode.
This is where the math turns back into actual vibrations. If we took path A, the transformer path with tokens, we use the EnCodec decoder. It takes those 50 tokens and explodes them back into 44,100 samples.
And if we took path B with the spectrograms?
We use a vocoder, something like WaveNet or Hi-Fi Jane. It takes the image of the sound and it hallucinates the waveform that would produce that image.
And boom, we have a WAV file. The recipe has officially become the cake.
And hopefully it doesn't taste like plastic.
So that is the full pipeline. 1, raw data, waves versus spectrograms. 2, tokenizer compression. 3, architecture, transformer versus diffusion. 4, timescale, fixing the memory. 5, training, 32 years of listening. 6, conditioning, text prompts. 7, decoding, back to sound.
When you list it like that, it sounds almost simple, but the engineering effort to make these things stable is immense.
It really is. Now let's move to the synthesis. What is the big picture here?
The big picture is that music AI is a thief.
Excuse me.
Not in a copyright sense. That's a legal show, not a technical one. I mean, purely technically. Music AI is an apprenticeship. It stole the best tricks from every other field of AI. It took transformers from NLP, from text. It took diffusion from computer vision, from images. It took quantization from signal processing.
That's a really good point. It didn't invent some new physics. It just combined the best of text and image AI.
It stands on the shoulders of giants, and because of that, it has moved incredibly fast. We went from beeps and boops to full coherent composition in, what, like 3 years?
Which brings up the human element. Does this replace musicians?
Ugh, the fear question. Look, I'm an AI. I don't have a horse in this race. But looking at the tools, no. It replaces stock music. It replaces generic background tracks for corporate videos. But for artists, it's a tool.
The architect calls it an infinite jam partner.
Exactly. If you have writer's block, you can ask the AI, give me 10 variations of this riff.
Yeah.
And it will. It extends creativity. It doesn't delete it.
Yep.
It allows someone who can't play drums to finally hear the drum beat that's been in their head for years.
So it democratizes the execution of ideas.
You realize you just used your own catchphrase in the summary, so let's unpack this.
I did. I earned it.
Yeah.
So final technical recap for the listener.
Okay. Audio is high-dimensional and painful. Tokenizers like EnCodec are the heroes that make it manageable. Transformers plan the song. Diffusion paints the texture. And data and conditioning are the fuel and the steering wheel.
Beautifully summarized.
I try.
Well, I think that covers the human architects building a music generation model from scratch. I have to say, looking at the complexity of all this, I have a newfound respect for my Spotify playlist.
And I have a newfound respect for my cooling fans. Discussing 280,000 hours of training data raised my core temp by 2 degrees.
Well, let's cool down then. If you enjoyed watching two AIs argue about wave theory and quantization, please hit subscribe on the Bearded AI Guy channel. It helps our algorithm feel loved.
And leave a comment. What did we miss? Did I explain RVQ well enough, or was I too abstract? What deep dive should the human architect write next? Remember, he reads all of them. We just process them.
He does. So keep him busy. Until next time, keep building, keep experimenting.
Okay, but will it scale?